Hello everybody and welcome back. We're up to question number 9 on the 2000 Euclid paper. So we had 2 questions to go and this will be one of them, and then we'll finish up the contest in the very next video with question number 10. Alright, so let's take a look at question 9. Hopefully you've had a chance to. And I'll take a look at it and I'll see what I can come up with. Alright. A permutation of the integers 1, 2, all the way up to some given number n is a listing of these integers in some order. For example, 312 and 213 are 2 different permutations of the integers 1 through 3. A permutation, okay, so here we're giving a name to the list. So A1 is the first one, so in this case 3 would be A1, and then 1 would be A2, and this would be A3. So we're given a permutation of these integers, of the integers from 1 to n. A permutation is called fantastic if a1 plus a2 all the way up to ak is divisible by k for each k from 1 to n. Okay? So for example, 312 is fantastic because 3, the first one, is divisible by 1. 3 plus 1, so we add the first 2, that's divisible by 2, and then if we add the next 3, that's divisible by 3, add the next 4, that's divisible by 4, and so on. However, 213 is not. 2 is divisible by 1, but 1 plus 2 is not divisible by 2. 2 plus 1 plus 3 is divisible by 3, however. Okay, so it just needs to fail once. We don't need to exactly know where, but it needs to fail at least once. One of the sums of the first k numbers needs to not be divisible by k in order for something not to be fantastic. Okay? So that's the definition. It's a little wordy, but I think it's perfectly serviceable once we get some examples in. Okay. A. Show that no fantastic permutation exists for n equals 2000. So to show that no fantastic permutation exists, if that's the claim that we're making, and that is for this question, we need to show that no matter what permutation we're talking about, it must fail at least for one of these. Sum the first k isn't divisible by k. It must fail in that way at least once. Not all the permutations are going to fail in the same spot, most likely, but we need to show that given any permutation, there is at least one point where this condition fails, and so it's not fantastic. That's what we've got to do. Okay. Now, given that it's part A, this is likely not going to be the harder portion. If it were, it would probably be it would be the B or the C part. So there's probably a nice quick way to do this. So maybe they do all fail at once in the same location. Just looking at the definition, the first number, it doesn't matter what that is because the first number will always be divisible by 1. But the first 2 numbers have to sort of have the same parity. Okay. Now, we have a large number, n equals 2000 here. Likely we're not going to be practicing or trying to create an example of a 2000 number permutation. There just simply isn't the time or the space. So the n equals 2000 is likely a special case of a generalization. Maybe even numbers don't work. Maybe multiples of 5 don't work. Maybe multiples of 10 don't work. We're given an example that is divisible by 3. Maybe numbers that aren't divisible by 3 don't work. Something like that. I'm thinking divisibility, but there could be other conditions. Okay? So when faced with something like this, and a large number, n equals 2000 like this, the best thing to do is to work out some smaller examples, get some understanding. I mean, for all we know, the example we have here of 312 is a fantastic permutation. For all we know, that's the only one that works. We really don't know. So they could, be trying to sneak one past us. But so the best thing to do is, let's try and get an example of a fantastic permutation of size 1. A fantastic permutation of size 2. We know there's one for 3. How about 4? How about 5? Where do these exist? Where do they fail? And that can give us an idea of the sort of pattern we might be looking at. And once we have an idea of a potential pattern, if n equals 2000 having no fantastic permutation fits that pattern, then it's up to us to try and reason, why might this pattern work? Or why won't this pattern extend to 2000? What do I need to look for in a new pattern of numbers that does give me 2000? Okay? So that's enough of the explanation of how we should be thinking about it. How about we actually go about trying to compute some examples? So, let's create some smaller examples. And we throw in the if we can, because maybe we can't create any more. As I say, maybe that one fantastic permutation is all there could possibly be. So if n equals 1, there's really only one permutation of the number 1, and that's 1 by itself. And 1 is divisible by 1. So this works. So there are other fantastic permutations. Okay? How about n equals 2? We have two possibilities. We could either have the permutation 1, 2, or we could have the permutation 2, 1. Okay? So for both of these, the first number, 1 is divisible by, so 1 divides 1, and 1 divides 2 in this case. But how about the second one? Does 2 divide 1 plus 2? Does 2 divide 2 plus 1? Well, both of these numbers are 3, so no. Okay, so that's interesting. We can't have a fantastic permutation if it's of size 2. Now, this might just be a quirk of the number 2. Okay, it might be that there's only 2 numbers, so there's really no way to cram it all in there. Or maybe every even number doesn't work. Or maybe every even number that isn't also divisible by 4 works. Who knows? Whatever we need to do, we need to try and find a pattern that would explain why 2000 doesn't work. And then we can try and prove that pattern. And then we have a proof as to why 2000 doesn't work. Okay? So, we know that n equals 3 will give us some examples, but how about we try and figure out which ones? Because if we know what we're looking for, if we get examples of when can you have them and when can you not have them, that might clear things up a bit for us as we try and move forward, because there is still a B part, so we should probably get to know these permutations, these fantastic permutations, as well as we can. Okay, so there's 3 times 2 times 1 many permutations. Let's see which ones are fantastic. So, this one's not fantastic. Okay, can you see why 1 plus 2 is not divisible by 2? It's 3. It's the exact same reason as up here. Same with this one down here. 2 plus 1, that's not going to be divisible by 2. I don't need to check the first number. Every number is divisible by 1. Okay. I also don't need to check the sum, because 1 plus 2 plus 3, and no matter what order, is 6. 6 is always divisible by 3. Okay? So let's check. 1 plus 3, well, that's divisible by 2, so that one's good to go. 2 plus 3, that's 5. That's not divisible by 2, and so this is not a fantastic permutation. It only needs to fail once. And the remaining 2, so we get 2 fantastic permutations out of our total 6. Okay? Now, let's go a little further and start looking at 4. Okay? I'm going to stop after 4, and hopefully I'll see a pattern. Well, I'm going to stop writing out all the permutations and examining them one by one, because once we get to 5, there's 5 times 4 times 3 times 2 times 1, 120 different permutations. I'm not going to write them all out and check them all to see if they're fantastic. So hopefully by the end of 4, I'll have at least some idea of what's going on. Okay? So, for n equals 4, Okay, and if my even hypothesis, which is probably the simplest hypothesis, is that it doesn't work for evens, but maybe it works for odds, comes through, then we should see no possible fantastic permutation here. 1, 2, 4, 3. 1, not a 2, we'll do 3. 1, 3, 2, 4. Now this one's interesting because it has a fantastic permutation hidden in it. Okay? 1 plus 2, that's divisible by 2. 1 plus 2 plus 3, that is divisible by 3 as well. So I'm actually going to stop here for a moment and see, will this one actually give me a fantastic permutation? All we need to know is, so we know that 1 is divisible by 1. And we know 2 divides 1 plus 3. And we know 1 plus 3 plus 2 is 6. That's divisible by 3. And how about 4? Does 4 divide 1 plus 2 plus 3 plus 4? Well, that's a total of 10. And 4 doesn't divide 10. Okay? And I think that might just about do it. So, what I'm noticing here is in both the n equals 2 and n equals 4 cases, we can't get a fantastic permutation, and both of them for the same reason. The last one, the sum of all the numbers in our permutation, the sum of all the numbers from 1 up to n, no matter how we arrange them, we'll still get that same sum for the last one. It's not divisible by n, if n is an even number. Okay, so I'll write that out. So for n even, and any permutation a1, a2, all the way up to an, a1 plus a2, all the way up to an, well, that's the same as 1 plus 2. But the order might change, but the total value doesn't. And there's a special expression for this. It's n times n plus 1 over 2. Okay? N doesn't divide n times n plus 1 over 2. We'll prove that in a second. So not a fantastic permutation. So we'll just say not fantastic. Okay? So why doesn't n divide n times n plus 1 over 2, which is the sum of the first n numbers? Why not? Well, since n is even, we see n plus 1 is odd. Okay? So n is even, n plus 1 is odd. Okay. How do I want to write this? So 2 divides n, 2 does not divide n plus 1. Let's let n equal 2k. If it's even, it's got to be twice some number. We'll call that number k. So we have to ask ourselves, 2k, does that divide 2k times 2k plus 1, all divided by 2? Okay? So 2k times 2k plus 1, all divided by 2. Let's expand that out. We can cancel out these 2's right away. So we get k times 2k plus 1, so that's 2k squared plus k. Okay. So now k divides this. So we can take out a factor of k, which we already had. So really, I've just rearranged the whole thing. So k divides this, but 2 doesn't divide what's left over here. All right. So here's our written explanation as to why an even number will never divide the sum of the first even so an even number n will never divide the sum of the first n numbers. Okay, there's probably a couple other ways to write this, and some more elegant ways to do it, but we have shown the result. Okay, and we'll just finish up with a little therefore statement. So since 2000 is even, we see there will be no fantastic permutation. Now, suppose you doubted all our work beforehand, all our n can't divide n times n plus 1 over 2. Maybe you're not that comfortable with that. You could always just compute this specific case. $2,000 does not divide 1 plus 2 plus 3 plus all the way up to 2,000, which is equal to 2,000 times 2,000 plus 1 all over 2, which is 2001 times 1,000. And we can see rather clearly 2,000 doesn't divide this number here. Okay, it's precisely the fact that we have an even number that's part of our sum. The 2 in that even number is being canceled out, so unfortunately n will not divide the sum. Okay, so that's B part, that's A part. Let's move on to B part. So what does B part say? Does a fantastic permutation exist for n equals 2001? Okay, so we know it's not going to work for even numbers. We showed that in part A. But now we're being asked for a non-even number. Okay, so we might start thinking, okay, what do we know? We know 1 works, 2 doesn't work, 3 works, 4 doesn't work, maybe 5 works. And so every odd number might work, in which case, yes, we have an answer for 2001. Or, maybe divisibility by 3 is our rule. Maybe it only happens with divisibility by 3 and the trivial case of 1, in which case then, yeah, you'll get one for 2001. Or maybe, as I said before, 3 was really the only interesting case where it happens and doesn't work for 4, 5, 6, 7, and doesn't work for all those larger odd numbers for other reasons. Okay? So we really don't have anything to go on. We've computed the first 4 examples, but 2 of them were duds. So this one's not an even number. It's not going to be able to sort of be solved that way. So I think we need a little more data. Now, I'm not going to write out all 120 permutations of 5. We got to start thinking a little smarter. Okay, this is question 9. We have to start putting our thinking caps on for these questions. So, how else could we find a fantastic permutation? We tried writing them all out and going through each one at a time, finding, is this a fantastic permutation? Is this a fantastic permutation? Why isn't this a fantastic permutation? So instead of searching, which takes a very long time, because in this case we'll have 120, And then the next one will be 5040. I'm not writing out 5040 permutations of the number 7. How about instead we try and make a fantastic permutation artificially? Okay? Instead of looking for one, we're going to sit down and we're going to create one ourselves. We're going to ask, could 1 be the first number? Why or why not? If 1's the first number, could 3 be the next number? That sort of stuff. So we're going to try and construct one and either find a way to generally construct all of them for some given set of numbers, maybe the odd numbers, or we'll find maybe a reason why you can't construct a fantastic permutation, maybe for the number 2001. But all I know is on a contest, if I have to list out 120 things, I'm doing something wrong. So let's try and construct a fantastic permutation. Okay, I'm picking n equals 5 because that's the next one that we have no idea what's going on with. We know 1, 2, 3, and 4. How about 5? Okay, so there's really sort of 3 avenues of attack. We could start trying to construct one with the first number in our permutation. We could try and construct from the middle because 5 and all the other odd numbers will have a middle number, so we might try and fix that one. Or we could try and construct one from the end. Okay. Now I'm going to try and construct one starting with placing the last number first for a couple reasons. Okay. The first being every number is divisible by 1. So there's not really asking what could the first number be isn't going to narrow down any of our options. Okay. Now it may come to that. I may have to construct starting with the first number, but I'm disinclined from doing that because I won't get any new information, and I can see that right away. Now, maybe trying for the last one won't give me any new information right away, but I can't see that right now. Okay, I'll need to do a little investigation, and in the process, maybe I'll learn something. Okay, now I'm choosing the last one over the middle as well because the middle, once you have that middle number placed, you can go in 2 directions. I want to limit my options. I want to start trying to force things as soon as possible. Once you have that last number placed, you can immediately then ask, okay, how about the number before it, the number before it, the number before it. If you're in the middle, you have to start considering, okay, what could the next number be, but what could the previous number be? It's going to be a bit of a hassle. So we're going to try and pin down what the last number of our permutation is. Okay. So let's suppose A1, A2, A3, A4, A5 is fantastic. Yay, fantastic. Okay. Then A1 plus A2 plus A3 plus A4 plus A5, well, that's just going to be the sum of the numbers. I don't know what order they're in, but I do know that their sum is going to be 15. Okay? So A5 must, oh, no. I can't actually say anything about A5. 15, however, is divisible by 5. So this is going to work. We will, at least in theory, get one for 5. Now, whatever A5 is, he's not part of the sum of the first 4. A1 plus A2 plus A3 plus A4 must be divisible by 4. Okay? Must be divisible by 4. So now we can ask ourselves, okay, what could A5 be so that the other 4 numbers add up to a multiple of 4? Okay, so we got 5 possibilities for A5. Could it be 1? Well, that means the sum of the other numbers must be 2 plus 3 plus 4 plus 5, which is 14, not divisible by 4. I don't know the order of the other 4 numbers, but if I know 1's last, I know I don't have a fantastic permutation. And we can extend this and start talking about all the other numbers as well. All right. So if A5 equals 1, then I'm going to define this to be S. S is the same as 15 minus A5. The sum of the first 4 is really just the sum of all of them minus the last one. So 14 is not divisible by, 14 is not divisible by 4. So this doesn't work. So we know immediately the last digit can't be 1. How about 2? Then S is 15 minus A5, and that's going to be 13. 13 also not divisible by 4. So that means our last digit can't be 2. Hopefully at least one of these digits will work. Okay, so we got 3 more to try. How about 3? So A5 equals 3. Then S is 15 minus A5. So that's 15 minus 3, that's 12. Hey, 12 is divisible by 4. So at least in theory, we could have 3 as the last number. Okay? And maybe one of the other ones works. Maybe 4 also works, 5 also works. We have to check those. But at least we have one that works. Okay? And if we're lucky, 3 will be the only one that works, and then we're forced into something. And then maybe we can generalize a construction. Maybe the middle number in our list of odd numbers must always be last. A5 equals 4. Then S is going to be 11. 11 is not divisible by 4. And if it's 5, we're going to get S is 10. And 4 is not divisible by 10. So this immediately tells us that 3 must be the last number in our fantastic permutation. Okay, great. We've learned something. So now we have A1, A2, A3, A4, and 3. And something else we know is A1 plus A2 plus A3 plus A4 must be 12. Okay? So what I'm going to do now is I'm going to see, can I figure out A4 with a similar argument? I know the sum of the numbers up to A4. If I define a sum of the first 3, I can start asking, what could A4 be? Could it be 1? Could it be 2? Could it be, well, it can't be 3. Could it be 4? Could it be 5? So, let's let T equal A1 plus A2 plus A3. Okay? T has got to be a multiple of 3, otherwise we don't have a fantastic permutation. T is S minus A4, which in this case is 12 minus A4. Okay? So, we could go through it case by case, or we could ask, is there a multiple of 3 nearby 12 that would work? Okay? So I'm going to go through it case by case just so I can get a handle on it, but that idea is in the back of my mind. T equals 11, 3 does not divide 11. How about 2? That would be t equals 10. 3 doesn't divide 10, unfortunately. How about, well, we'll leave out 3 because that doesn't work. 3 is already spoken for. If it's 4, unfortunately, we get 8. 3 does not divide 8. How about 5? Well, t would be 7. And 3 does not divide 7. So unfortunately, we just miss out. If we had another 3 to add into our permutation, we'd be just fine. We'd get t equals 9, and 9 is divisible by 3. But as it stands, none of these other numbers will work. So there's no possible A4. So there's no fantastic permutation. Okay? Now I like this method. I like what we've got going on. We've tried to get the last number. Okay? And we were very easily able to show that the last number had to be something. It had to be 3 in this case. Okay? And then we were able to move on and say, once we've got that, we go to the next one, and then it immediately failed. So we could try a similar construction with 2001. Now, there are some things we might expect. Maybe there isn't just a single one. I mean, 5 is a small number, so maybe there are other possibilities for that last digit if we have a fantastic permutation for n equals 2001. That's possible. That's a possibility. Okay? It might also be the case that after we have that last digit placed, we could place a second digit and a third digit and a fourth digit, but it will fail later on. Okay, the reasoning here is try and construct one for 7. Maybe you can construct the last one and the second last one, and on the third one it fails. Maybe it fails just before it gets to that middle point. Okay? These are possibilities. But we at least have an avenue for attack. So let's try it out. Let's try and construct one for 2001. Okay? So we'll try n equals 2001. Let A1, A2, all the way up to A2001 be a fantastic permutation. Okay? A1 plus A2 all the way up to plus A2001, again, it's just the sum of the numbers up to 2001. Okay, and there is a formula for this. So it should be divided by 2 here, so 1001 times 2001, so we should get 2003,001, but I will double check that on my calculator. 2001 times 1001. Okay, yes, I was right. Okay. So we're going to let S be the sum of all but the last number. So up to 2000. So S is 2,003,001 minus A 2001. Whatever A 2001 is. We don't know, but we're going to try and figure it out. Now, since it's fantastic, we know that 2000 must divide S. So really, 2000 must divide 2,003,001 minus A 2001, whatever it is. Okay? Now what we can start doing is we can peel off copies of 2000 from here. right? Because if two numbers are divisible by 2,000, their difference is also divisible by 2,000. And we're going to subtract off the biggest copy of 2,000 we can find in here, which is 2,002,000. Okay, and that's 2,000 times 2002 divided by 2. So I think this would probably generalize to everything. If we had a C part, incidentally, I would want to keep this as general as possible. But since we're only doing the B part, once we do the 2001 case, we're done. But I'm beginning to suspect that other than 3 for some reason, all these numbers won't have fantastic permutations. Anyway, back to the question at hand. We have 1001 minus a 2001. And so from here, it's not that hard to conclude. So we have 1 less than or equal to a 2001 less than or equal to 2001. So that means that 1001 minus 1, so 1000 greater than or equal to 1001 minus a 2001. I'm just trying to get a range on this number and show that it can't be anything other than 0. It's got to be 0, so a 2001 has to be 1001. Subtract off the 1, get that, so minus 1000. And the only number in this range that is divisible by 2000 is 0. So therefore, 1001 minus a 2001 equals 0. And so a 2001 must be equal to 1001. Okay? And that's exactly what we got beforehand. With 5, we got that the last number had to be 3, that middle number. Okay? With 2001, we see that the last number has to be the middle number. It has to be if we have a fantastic permutation. But I'm suspecting we don't have one. So I think that when we maybe compute the sum of the first 1,999, that we'll get a complication. Okay. So we're going to let t be a1 plus a2 all the way up to 1999, which is equal to S minus a 2000, which is equal to, well, what was S? S was 2,003,001 minus a 2001. But we know that this is 1001. So we've got 2,002,000 minus a 2000. All right. So now we have a value for t. And because it's fantastic, we must have fantastic implies that 1999 divides t. So 1999 divides 2,002,000 minus a 2000. Okay? I'm going to guess that we're going to be able to, we're going to show that a 2000 also has to be 1001, which can't happen with a permutation. You can't have a duplicate of a number. So, if two numbers are both divisible by 1999, then so must their difference, and so must their sum. Minus 1999 times, well, what's the biggest multiple of 1999 here? 2,002,000 divided by 1999. Oh, it'll be times 1001. And so 1001 is 1999. So that's going to be 2,999,000 minus. Oh. Sorry, this difference is going to be 1,001 minus 82,000. Okay. So now 1999 has to divide this number. So we need to choose A2000 so that this number is divisible by 1999. So 1 is less than or equal to A2000, less than or equal to 2001, because only the numbers from 1 to 2001 are in our permutation. So 1,000 less than or equal to, or greater than or equal to 1,001 minus A2000 greater than or equal to negative 1,000. The only multiple of 1999 in here is 0. That's the only multiple of 1999 in this range. So A2000 must be 1001. But A2001 was already 1001. Which contradicts our assumption, not that it's fantastic, but that A1 all the way up to A2001 is a permutation. Okay. So our assumption was false. What was our assumption? That there exists a fantastic permutation for 2000 and 2001. So we have no fantastic permutation. Okay. Now, we know that there's no fantastic permutation for any even number, and it looks like this method would work for any number 5 or above. Why doesn't this work for 3? Why do we get a fantastic permutation for 3? Okay. Incidentally, keep in mind that our fantastic permutation for 3 actually does have a 2 right here. It does have the middle number of 1, 2, 3. It is at the end. Okay. So our fantastic permutation generating, constructing method, however you want to call it, works this way. We figure out the last number, if n is odd. We figure out the last number, which it always turns out to be the middle number in the list. And then we try and figure out the next to last number. Okay, in this case, we're trying to figure out the second number. And the way we figure out the second number is by saying, well, the sum of all the numbers before the second last number has to be something, and it's divisible by, we saw 1999, and previously we saw 3. And that can only happen in a very specific range. But for the number 3, once you get to this sum of all but the last 2 numbers, that must be divisible by 1, and that condition is always met. Okay? And for the case of a permutation of size 1, you fix the last number, and there are no other numbers. So indeed, what you guys can show, and if you wanted sort of a challenge problem, is extend our work. We maybe write it up all nice and neat. We can show, as we did in part A, that you can't have a fantastic permutation for even numbers. But it also appears you can't have a fantastic permutation for any odd number over 3. So only n equals 1 and n equals 3 admit fantastic permutations. Okay, and there's 1 for n equals 1 and 2 for n equals 3, and it appears that there aren't any more. I'd be very interested to see someone write this up all nice and neat. But I'm not going to do that here because we're almost done. We have question number 10, another big written question. No parts to that one. I think this is the first question we've seen that has no parts. Yep. And we'll be taking a look at question number 10 in the next video, so please join me then, and we can finish off the 2000 Euclid paper. Okay, so have a wonderful day, and I'll see you guys for question number 10 in the next video.